Hey everybody, so this is the last videos for the study guide. So we're going to start with Unit 4, Skill 1, Endo and Exothermic Graphs. So when you have a reaction diagram, that's basically a graph that's a potential energy graph versus reaction progress, which is time. So basically what happens to the potential energy to the chemicals over time, and it shows the energy of your reactants and your products. And when the reactant has more energy compared to the product, it's an exothermic reaction. This means that the reaction has a negative delta H, and that heat is being released to the environment. So the actual system is starting to cool down because it's releasing that heat. On the other hand, when the reactants, this should say, there's a typo here, so sorry about that, have a lower energy compared to the product, it is an endothermic graph. Or an endothermic reaction, represented by the endothermic graph. And this means that the reaction is going to have a positive delta H because it absorbs energy from the environment. And if it's absorbing energy, that means it's going to start to heat up. The temperature will increase. And so when you have a graph like this, a reaction diagram, for this question, we wanted you to label all the different parts that you could. So we've got A is the energy of the reactants. And on both graphs, when you have reaction progress, that means you kind of have like the beginning of your reaction is over here and the end is on the right side. So your reactants are the energy of your reactants is from 0 all the way to where that line is. So that would be A. So the energy of the reactants for this first graph would be 120 kilojoules. And for this one over here, you can see it's much shorter. So that's like the big difference in the type. So here our energy of our reactants is much higher than the products. So this is our exothermic graph. Whereas on this one on the right, the energy of the reactants is much lower than the energy of the products. So this is endothermic because it has to absorb energy in order to get up that high. And so kind of like I alluded to, the energy of the products is right here. So it's very small in an exothermic graph, but pretty big in comparison on an endothermic graph. Our activation energy is something we talked about in Unit 5 with these graphs. It's the energy to get started in the reaction. And so that goes from basically the top of this hill to where the reactants start. That would be C. And you can see that that's actually a pretty large amount in an endothermic graph. And my arrow's not very good there. Let's try that again. So that's about that distance there for the endothermic graph. So you can see it has to absorb a lot of energy in order to get started. So then E, which is the total energy of the reaction, that's the top of the hill all the way to 0. So in this case, that would be 210, or in the case of an endothermic graph, or this particular one, it's 38. But the top of the hill really just measures the total energy, or the highest energy that it will reach. And then your change in energy for the reaction is called delta H. Now remember, for an exothermic reaction and endothermic reaction, one will be positive and one will be negative. So what you do is that would be the energy from your reactants to your products. That'd be this distance here. So that's our delta H. And it's always your products minus your reactant. So that would be 25 minus 120, which would give you 90 negative, let me make sure that's a little more obvious, negative 95 kilojoules. And so that negative is telling you that 95 kilojoules was released into the environment. Whereas here, our delta H, I'll kind of do this over here. Our delta H would be products minus reactants, so that would be 30 minus 8, which would give you 28 kilojoules for our delta H. And so that's kind of everything labeled, all the pieces of information that you could get from there. Just keep in mind that not all of them start at 0, so just keep an eye on that. Now, if we look at just kind of endo and exothermic concepts in general, remember that a physical change can also be classified as an exothermic or endothermic process. It doesn't just have to be a chemical reaction. So for example, if you have a phase change, like you're going from solid to liquid, liquid to gas, you're melting, those are all phase changes or physical changes. And they involve the transfer of heat energy. So in an endothermic phase change, such as vaporization, when you're going from a liquid to a gas, your energy is being absorbed. And you know that energy is being absorbed because to go from a liquid to a gas, it has to heat up, for liquid to turn into steam. So the energy is absorbed to the system, and the molecules are going to speed up. Okay, so when energy is absorbed, the temperature is going up. Remember, temperature measures the speed of the molecules, so they start to speed up. Whereas during an exothermic process, like freezing, where you're going from a liquid to a solid, energy is being released because those molecules it has to cool down. So it releases the energy, and so the molecules slow down, which is reflected in the temperature. So when we look at these different phases, we want to label them as being exothermic or endothermic. And I just always think about, is my temperature going up or is my temperature going down? Now, for my ice cream to melt, that means the temperature is going up. And we know this is going from a solid to a liquid. So that means that this is an endothermic process. And I meant to draw an arrow here. Temperature is going up. For freezing, okay, that's the reverse. That's when you're going from a liquid to a solid and the temperature is going down. So that makes this an exothermic process. Now, for condensation, that's when we go from a gas to a liquid. That's when you see the condensation kind of on the outside of your glass if it's a cold glass on a warm day. And the temperature has to cool down because you're actually cooling down the water that's in the air around your container. And so that would make this an exothermic process because the heat in the air is being released into your cup, right? Your cup starts to warm up, but the air around it is a little bit cooler. And then vaporization is the reverse. It's going from a liquid to a gas, just like we talked about earlier. It's steaming. The temperature has to go up. It's vaporization. One of the processes is boiling. And so this is endothermic. It has to absorb heat in order for this process to occur. So that is the basics of endo and exothermic processes. And we will get into the math of heat calculations in the next video.